What's up guys? Today I'm going to be showing you how to use the substitution x equals e to the u to reduce reducible differential second order equations. So if you're watching this video, you're probably familiar with the normal form of differential equations, where you have a plus b plus c times the derivatives going down, and you'll have an fx if it's non-homogeneous. You're probably familiar with how to solve this. You know y equals e to the mx, and then particular integral if it's non-homogeneous, and then you solve and there's three cases. But now, what if that wasn't the only case? What if, as well as this format, you had an ax squared in front of the second derivative and an x in front of the first derivative? That's what this substitution helps with. So our ultimate goal is to get this equation back into the normal familiar format, but with a different variable in terms of u, not x. So where do we begin? Let's say this is our equation, and I'm just setting all the number coefficients to 1. In reality, if they're anything other than 1, you can just put them back in when we substitute everything at the end, and it makes no difference. So we're going to just go with 1, so you can get the concept. X equals e to the u is the substitution we're going to make. So let's begin. The method comes in two steps. Find the first derivative and find the second derivative using the first. So the first derivative, we want to get x times the first derivative into the format of something with dy by du. I'm going to give you a bit of a spoiler. They're actually equal to each other already. So all we have to do is prove that dy by du is the same as x dy by dx. It's a bit odd in that you start with the thing you're trying to prove. So you start with dy by du. And we're trying to get this in terms of dy by dx times something. So it would make sense to introduce a dx term into this, and that means we're going to be using the chain rule. So let's introduce that. Dy by dx times dx by du. Now, we're already halfway there. So we've got dy by dx, and dx du, well, if you look at the substitution we made, you'll see that dx by du is also e to the u, which is also x. So we've already proven, basically, that dy by du becomes dy by dx multiplied by x. Great, that's all we had to do for the first derivative. Now for the second derivative. D squared y on du squared. This, a normal way of writing this is just d by du of dy by du. In other words, the derivative with respect to u of the first derivative. That's totally standard and normal, right? And we also know what the first derivative is already, so I'm just going to write in what the first derivative was. X dy by dx. In fact, we don't even need the x there because we're differentiating with respect to u, so it would just make it easier to leave it as e to the u. So let's do this derivative, shall we? If it looks like a product rule, it probably is. So we're doing it by the product rule. First part is fairly self-explanatory, just because we've got e to the u, and that's its own derivative. The second part is a bit more odd. So obviously we're going to have e to the u multiplying something, but now we're tasked with differentiating dy by dx with respect to u. This is where 95% of people blunder. So what we're going to do from here, because you can't actually do d by du of this thing, we're going to do it with respect to x. Because differentiating with respect to x of that derivative is very simple. That's the second derivative. We've been doing that since year 12. So what we're going to do about the other stuff, so that we can make sure we're still differentiating with respect to u instead of x, we're going to multiply by dx by du to get rid of the dx and keep the du there, so that it just works with the sort of mega chain rule. As you can see, the two fractions on the left-hand side cancel out to d by du of dy by dx. So now if we do the two in the middle, we've got dy by dx, and that's derivative, so let's just do that. And we have dx on du, d squared y on dx squared. And this is really promising, because we've got the second derivative in terms of x, and we have some terms that look suspiciously like they could become x. So let's keep that part, and put it back into our formula. Do you see the magical substitution that's about to happen? We've got e to the u and dx by du. So when we put these together, we already know what they are. They're x. And look at that, we've got x squared. And this first term we've got on the left over here, well, that's already in terms of u's, remember? We artificially took it back into dy by dx. So if we just put it back, we've got dy by du. And this is all what our second derivative is equal to when we're differentiating with respect to u. So cheeky bit of rearranging, and we've isolated the x squared term. So now it's just a case of substituting everything back in. That is what that becomes, and the first derivatives cancel, so we've just got this. A friendly equation that you know how to solve. I'm just going to do it really quickly to get to the final point. The final point is you can't leave the substitution as it is. You have to like put it back. So x equals e to the u, so u equals ln x. And that, ladies and gentlemen, is the final answer. Peace.